My name's Chhi'mèd Künzang. I work at Protocol Labs. I led the team that created the Filecoin proofs. In doing that, we created a really high-performance, really high-scale system using zero-knowledge proofs, or SNARKs. And in that, we came to discover how inadequate the previous generation of SNARKs were that we used. There are all kinds of limitations, and they're really, really hard to write, and they're really hard to get correct. So this work represents something that I got interested in after having done that, which is how can we do better. Recursive SNARKs are something that are now possible that weren't at that time in a practical way. So I said, how can we exploit that? And how can we get good systems that are easy to program? So the title is Turing Complete Expression Evaluation for Recursive SNARKs. That's what I'm going to talk about. OK, so I said before, LIRC is my word. That's the name of the language that we've created. LIRC is a Lisp. You execute a program by evaluating an expression. So every expression is just some piece of data that, according to the programming language's rules, evaluates to some other piece of data, possibly. And it can be proved using recursive SNARKs. The important thing about the recursive SNARKs there is that we're not limited to bounded-sized computations, which normal SNARKs are. For example, in Filecoin, we could do really large Gros-16 SNARKs, which was like 100 million constraints. That was really big for SNARKs, but it's not really big for anything you might want to compute. LIRC is a data language, so all expressions in LIRC basically have a hash and a type tag associated with them, so they're content addressable. They're the kinds of things that you can stick on IPFS and reason about. So any expression can be evaluated, and then we can generate this succinct proof, which means the proof is going to be small, on the order of kilobytes, and it's going to be fast to verify. Less than a second, maybe 30 to 50. I can't tell you right now what it's going to be in practice, but tens of milliseconds to verify, no matter how large the thing you're proving is. And as I said before, content addressed, and it's Turing complete, so there's no bound on recursion. So anything that we can express in computation that's deterministic, that is Turing complete, we can do in LIRC. We can also do more than that, kind of as was hinted at in an earlier talk, but I'm only going to talk about the deterministic Turing complete part today. And so because of this, we can nest these things infinitely. We can have recursive data structures and recursive computations over those. And then however big those are, we can still come up with a short proof. And the proof reveals nothing about the inputs. So we can say, well, here's a value, and I don't know what it is. And here's the output, and I don't know what that is. But I can tell you it was derived correctly according to the language. And then I can reveal just enough about what that program was that you're satisfied that it meets your needs, but not giving away something that I don't want to tell you. So I'll tell you a little bit about things that are being built on LIRC to give you an idea about how powerful it is. Wow, I'm halfway through. So there's a company called Yatima who's doing a lot of work with this. They're building a Lean-4 theorem prover kernel implemented in LIRC so that basically you'll be able to do arbitrary theorem proving and get succinct proofs out of it. Even if you don't care about zero knowledge, this is cool because the verification of large theorems is a bottleneck. So here we can potentially have an infinitely growing set of theorems that have been proved that depend on each other and still have constant time verification. In current work, they're working on bringing this to the FVM, which is going to be the Filecoin virtual machine. We're going to have smart contracts that can execute LIRC. WebAssembly and EVM interpreters that can also do this. So we can use LIRC as a building block in that way. There's a company called Glow that has a high-level language for generating smart contracts that cover a whole interaction and give you formally verified properties of the interaction, and they're using LIRC as a back end. OK, and now this is just the speed run through things that LIRC can do to give you a sense of what it feels like. Might feel really high level if you're thinking about the crypto, might feel really low level if you're thinking about programming languages. This is where it just becomes a flip book. I'm just going to show you stuff and try to get through about 80 slides in 2 minutes. OK, so you have lists. You look at the first element of the list, it tells you what you're doing. OK, 2 plus 3 is 5. Cons means construct. We make a pair. We use hashes for this. So this is how we create these Merkle data structures. We can make arbitrarily shaped trees of data like this. And it doesn't just have to be pairs, but that's what I'm showing you here. We have conditionals, so we don't have to evaluate both branches, which is an important part of this Turing completeness. We don't have to have incredibly expensive computations when we're doing a lot of branching. And that's what's being shown here. This iteration count, that's basically how many clock cycles of reductions does it take to make a computation. So depending on which path we take, it takes 8 or it takes 6. So we're not following every branch. We have lexical bindings, just like any proper programming language does. And we can create anonymous functions. This is where Lurk starts getting cool. This is not what you get out of the box with most SNARK programming languages. And this is what really, to me, is the exciting thing, is we're building a language for expressing these programs that can be implemented in many backends. Right now, we have a GROS16 and a Nova backend. We'll probably have a Halo 2 backend in the future. And when somebody else makes a cool new proving system, we'll use that too. So functions are literal. We can immediately apply it. So here's a squared function being applied to 5. We get 25. We can name them. Here you go. We have closures. So we can do this classic functional programming make adder thing. We make an adder 1. We make an adder 9. And they work differently. We can make recursive functions if we explicitly say that we want to do that. Here's something that counts the length of a list. I got 14 seconds. Check this out. Look at that. We can do commitments. We can do functional commitments. With functional commitments, we have higher order functional commitments. We can commit to a function that takes a function as input and applies that function to data. We can do private functions, fair application of a credit bureau score, or do the same thing over private data by passing in the function to the committed function that knows about the data. Thanks. Well, and I know I'm over, but if you want to read the blog post, I'm told that it's going to be up later this afternoon, and it goes into a lot more detail.
Stay up there because we have time for questions.
Oh,
So you said it was RLTS based, it's Growth 16, right?
What's that?
It's Growth 16, it's using Growth 16 as a proving scheme for now?
Actually, Nova is the preferred one, and we do have Nova support now. But we did the first version of GROS16 because I know GROS16, and that's what we could do today. So it's not actually recursive, but we use SNARK pack and input aggregation.
Any limitation? Like, can you switch to long starts?
Well, I mean, like I said, we can implement Halo 2, and it'll actually be data compatible with Nova because we use the posture curves on purpose for that reason for Nova. The problem with GROS16 is you don't get true IVC, so the memory grows as the computation grows. With Nova, memory is constant, same with Halo 2.
Yes.
If you're using the GROS16 implementation, can you pick whatever curve you want?
Yeah, you could. You could. You'd have to run a trusted setup.
Right.
Yeah. Yeah.
And while I bring up the slides, we have one more.
One more.
Any reason behind list for program zero knowledge thing?
It turns out that McCarthy's original 1960 Lisp that gives you 5 primitives is enough to give you a lambda calculus-like thing, and it gives you all the things that you want. Plus, there's this rhyme between cons as the fundamental memory allocator and RAM machines, so it all worked out. Plus, Lisp was cool.
Wow. Wonderful. Thank